Hey Math 206, we're working on section 14.4, which is surface area of three-dimensional objects. So first, let's talk about surface area versus lateral area. So usually with prisms and things, we would talk about the top and the bottom. We would call those the bases, top base, bottom base. And then the lateral faces would be usually they would be rectangles of your shape, or if you have something that's not a right prism, they might be parallelograms. So calculating surface area really helps us to look at the nets of these 3D objects. So let's find some formulas. For a cube, for instance, you have, top and bottom, and then 1, 2, 3, 4 lateral sides. So that's 1, 2, 3, 4, 5, 6. That is 6 squares that make up the cube, right? So the surface area would be 6 groups of the area of one of these squares. So if you called the side length, say E, it would be E squared. Now, if you had any other prism that wasn't, perfectly symmetrical, you would have your top base and your bottom base, top and bottom, and the lateral rectangles that can be kind of all folded out to one long rectangle. So the surface area of a prism like this would be 2 times the area of the base plus this lateral surface area. Now the lateral surface area, the length of this rectangle would be the distances around the sides of your base. So that would be your perimeter times, so that would be the length of this rectangle. That's P for perimeter, times the width of this rectangle is the height of the prism. So now, for example, I've got a right triangular prism here. The area of the base would be 1/2 the base times the height. So 1/2 the 2 legs of this right triangle, 3 times 4, which is 6 square centimeters. And now the lateral area would be the perimeter times the height. The perimeter of the base here being 3 plus 5 plus 4 times the height, which is 10. I think that is 120 square centimeters. So then the surface area now is twice the base, 2 times 6, plus the lateral area. So 12 plus 120 is 132, and then square centimeters. All right, now similarly, let's look at the surface area of a cylinder. Now this is a little bit different from a prism, but the same idea is that you have a top base and a bottom base. And then if you cut through the side of the lateral surface here and unroll it, you'll see a one long rectangle. And the dimensions of this rectangle, the height is the height of the cylinder, and the length of this lateral rectangle is actually the distance around the circular base. So with a prism, we call that the perimeter, but with a circle, you call that the circumference. So the surface area of a cylinder will be twice the base, 2 times the area of the base, plus the height times the circumference. So now with a circle, usually you're given what the radius of the circle is. So 2 times the area of the base. The area of a circle is pi r squared. So this would be 2 times pi r squared. And the circumference of the circle is 2 pi r. And then times the height. So this gives us a really nice, neat formula, 2 pi r squared plus 2 pi r h. And if you wanted to, you could make this even neater by factoring out that common factor of 2 pi r. So 2 pi r times r plus h. This would be the surface area of a cylinder. Now, again, I don't think it's important to memorize these surface area formulas. What is important is to understand where these formulas came from and being able to recreate it when you need to. All right, next let's find the surface area for pyramids and cones, which are, again, very similar. With a pyramid, you have one base, and then you have the lateral surface, which ends up being these triangles. The lateral surfaces are triangles. So this is a net of a square pyramid. So what the formula ends up being, the surface area of a pyramid will be the area of the base plus the sum of all the lateral triangle areas. Okay, so now if you are given a regular pyramid where the base, if the base is a regular polygon, of, say, you have n sides to it, and suppose you're given the slant height. Here L is the slant height. So not the height of the pyramid itself, not going from the apex down to the middle of the base. It's following the slanted lateral surface there. Then the area of each one of these triangles, if it's a regular, if the base is a regular polygon, then each of these triangles are congruent. And each of their areas is 1/2 the base, which I'll call B for the base of the pyramid, times the height. And the height of this triangle is really the slant height of the pyramid. So the surface area would be the area of the base, which in your book they call it a capital B, plus you've got n of these triangles, n times 1/2 B times L. So I'll write it like this, n times B times L over 2. And then we notice that n times B, the number of sides times the length of each side, is really just the perimeter of the base. So you could even simplify this by calling the surface area the area of the base plus 1/2 times the perimeter of the base times the slant length. And let's see what that looks like with these numbers. All right, so here's a square pyramid, and the area of the base, so if I wanted to calculate this, the surface area, I'd take the area of the base, which is 4 times 4, which is 16 square centimeters, plus I'll calculate 1/2. The perimeter, 4 plus 4 plus 4 plus 4 is 16, times the slant height, which was given to me as 5. So that gives me 16 plus 40, or 56, and my units are square centimeters. All right, now let's compare lateral, or the surface areas of two pyramids using all this information that we know. The Great Pyramid of Cheops is a right square pyramid with height of 148 meters and a square base with perimeter of 940 meters. They also give us the altitude of each triangular face. All right, so let's sort of draw this out, the information that they've given us, and make sure that we have enough information. So here is the pyramid. They tell us the perimeter of the base, P equals 940 meters. All right, and they also tell me the altitude of each triangular face is 189 meters. So here's the triangular face. The altitude, again, is basically the same as the slant height. So that slant height is 189 meters. So notice I'm not going to need the height of the pyramid itself to calculate the lateral surface area, because all we want to do is find out how the lateral surface areas of the two structures compare. So I'm not going to worry about the area of the base. The lateral surface area here will be 1/2 times the perimeter, 940, times the slant height, 189. So if we calculate that, 940 times 189, and then divide by 2, we get 88,830. And that would be in square meters. Now let's calculate the surface area, the lateral surface area for the Transamerica building that's in San Francisco. And so again, we have a square base. And it is a right square pyramid. It has a height of 260 meters, and the perimeter of the base is 140 meters. And they also give me the altitude of each of the triangular faces. So let me go ahead and draw in the apex. And they give us the altitude again here, which is the same as the slant height, which is 261 meters. So notice the perimeter here is much greater. The slant height is smaller. Here I've got a larger slant height, much smaller perimeter. So here the lateral surface area will be 1/2 times the perimeter times the height. So calculating that, 18,270 square meters. So now this problem asked me to compare these two. Obviously, the Great Pyramid is much larger than the Transamerica building. But how much larger is it? Is it twice as big, 3 times as big? We can calculate that by taking the ratio of the two surface areas, the lateral surface areas. We'll take 88,830 over 18,270, and let's see what that ratio is. Approximately 88,830 divided by 18,270, we get approximately 4.86. I'll say approximately 4.9. So we can say that the Great Pyramid is about 4.9 times larger in lateral surface area than the Transamerica building. So again, I like this problem because not only did we have to do some calculations, we had to do some comparing, and then it's good to say, how do we compare these two areas? One way to do that comparison is to look at the ratio between the sizes.